Då hälsar jag deltagarna som har loggat in här på Bergdagarna Online hjärtligt välkomna. Det är den sista av sessionerna för de online-presentationerna från bergmekanik och bergteknikdagen. Och idag är det bergmekanikdagen som har möjligheten att presentera den inbjudna gästföreläsaren Gabriel Walton från Colorado School of Mines, USA. Och det är då den sista av Bergdagarna online. Ser ni min skärm så i visningsläge? Jag är lite osäker på det.
Ja, det gör vi.
Ja, tack. Nu ska vi se. Ser ni mötesformalia nu? Eva, kan du ge mig respons på det?
Nej, inte ännu.
Nej. Jag är lite osäker på om jag har... Så visa skrivbordet här då. Så, ser ni mötesformalia nu?
Ja.
I visningsläge?
Nej.
Inte det. Det var ju värst och det var svårt. Okej. Jag har två skärmar så det kan bli lite konstigt där. Så.
Ja, nu funkar det.
Nu är det den, precis.
Ja.
Så, då är det lite inledande mötesformalia. Problem med anslutningen. Då provar ni att koppla ur och ansluta igen. Och under presentationen här så ber jag ha mikrofon och kamera avstängda. Som vi brukar ha så är det frågor ni kan ställa i chatten. Och sen så kommer jag då välja några frågor som föreläsaren får svara på. Och skulle vi få ont om tid så besvaras det skriftligen per mail. Och det kommer då publiceras på hemsidan. Vi har rätt gott om tid också. Jag tror vi bör hinna med rätt många frågor. Webbinariet spelas in och finns att lyssna på och se på Svenska Bergteknikföreningens YouTube-kanal. Och jag ska bara säga det att när ni ställer frågor på chatten så kan ni gärna ha det på engelska. Vi kan översätta, men det är lite bättre om ni kan formulera på engelska, så är det lite lättare att ställa frågorna till Gabriel Walton. Så det här var en inledande öppning här som jag gör Per Tengborg från BFO, Stiftelsen Bergteknisk forskning. Och nu ska vi gå in och bjuda in Gabriel Walton. And I just want to present Gabriel. Very welcome to us. Gabriel is a PhD in geomechanics from Queen's University and employed now as an assistant professor in geology and geological engineering at Colorado School of Mines. So very welcome, Gabriel, and I hand over to you.
Great, thank you so much. Thank you all for being here today, and thank you to the Swedish Rock Engineering Association for giving me the opportunity to present to you all. So I'm going to be speaking to you today about advances in bonded block modeling, some of the latest and greatest involving what we've been doing in our research group recently. I'd like to start by acknowledging my co-author, Dr. who's currently working with me as a postdoctoral researcher, but a majority of the research I'm going to be presenting today was part of his PhD thesis. Asan Gazvinian from Itasca, Minneapolis helped with the proofreading of the paper, and then Itasca Consulting Group provided some educational licenses which were used by Sean Keneal as part of his PhD. So when I'm talking about bonded block models, I'm really talking about models to help us understand stress-driven damage processes. And before getting into the technical details, I'd like to take a step back and just remind us all of one of the many reasons why we might be interested in understanding this better. This plot here may be familiar to some of you. It's showing the undercut depth for block caving mines over time. And what we can see here is that, heading into the 21st century, we've had a big increase in the depth of mining, and that's not unique to block caving mines at all. So as we go deeper, of course, that means higher stresses, and that presents new challenges operationally and for ground control. Now, when we think about how we might meet these challenges, we really have three main classes of design. For analytical, in many cases, that's simply not going to apply because our analytical solutions impose too many constraints that really move them far away from reality. If we think about empirical solutions, these work great, but of course, their limitation is that they are most appropriate or work best in scenarios that are similar to the cases that were used to develop them. And when we look at some of the common empirical systems that we use for design, the reality is that most of our experience that these were based on is in shallower cases where potential failure modes are more so gravity driven than stress driven. So again, as we move to these new, deeper, higher stress environments, these may not be always applicable. And so, of course, we can turn to numerical approaches, and these are, commonly state of practice now. You can see on the right an example of a finite difference model being used to look at stress transfer around a three-dimensional set of mine workings. And of course, we can use this for any number of things, including optimization of mine layout and sequencing, as illustrated on the bottom left here. Now, these are very common at the mine-wide scale, large elastic continuum models, just to understand stress transfer around excavations. But when we think about them in the context of understanding damage processes at a finer scale, really at, say, an individual pillar scale, for example, there are two major limitations. The first is that if we want to replicate these damage processes with continuum models, we really need to use some pretty complex constitutive models to replicate observed behavior. And at some point, these models become so complex that we can end up in situations where the parameters basically just become a series of knobs. And if we have enough knobs to turn, our model can sort of do whatever we want it to. So this is a quick example of that, of an under-constrained model. This is from the AECL mine by tunnel case study in Canada. What you're seeing here on the left in the red is the observed damage zone extent in situ. And then these four gray areas overlapping with that are the results of four different FLAC models. And what I'm showing here is that all of these models present basically equally good matches to the observations, but we can see that the model parameters that are associated with each of these are very different. So this is an illustration of that non-uniqueness problem that we can run into with some of these complex constitutive models. Now, when we talk about bonded block models or discontinuum models, those are also relatively complex, and so a similar potential limitation could be noted there. But when you think of all these different discontinuum models, bonded block, grain-based models, combined finite discrete element method, they do have an interesting basic principle that I think is inherent in a lot of their promise for future application. And the idea really is that unlike a continuum model where we're sort of coming up with a pseudo-empirical constitutive model to describe the emergent behavior, we can actually start with fundamental physics like Newton's second law and fundamental material properties more at the elemental level at a finer scale, and ultimately end up with realistic emergent behavior. And the concept is that if we have these more fundamental building blocks, then we could ultimately calibrate these models to lab data, upscale the parameters of these calibrated models to the engineering scale, and then actually make some reasonable in situ predictions without having to do a huge amount of calibration. Now, this upscaling here, right, is the key part, and I'm not really going to touch on that today, but I think the concept that these models can be upscaled is really some of the value added for them. The other limitation of continuum models is that while they're really good at assessing how support is going to respond to ground deformation, they're not very good at telling you how ground deformation is going to respond to the influence of reinforcement support. So I have a couple of examples to illustrate that. The first is a case study from the Creighton mine, which we'll actually talk about in a little more detail later on. This is the mining area that we were looking at and a particular pillar of interest. And you can see here the support pattern, a dense rock bolt support pattern that was installed in a numerical model for this mine. And what I'm showing here is basically illustrating that lack of influence of the reinforcement elements in the continuum model on the model results. So these are the displacements in two different directions, and we can see that whether we have that very dense bolting or whether we simply leave the bolts out, the ground response is basically the same. This is another illustration of that same phenomenon. We wanted to look at, is this limitation just something to do with the structural elements, for example, that are implemented in FLAC 3D? And so we developed this hypothetical pillar case on the right, where we're loading it monotonically, and we tested three alternative cases, one with no bolt installed, one where we installed the cable bolt element, so that same structural element used in the previous case. And then in the third case, we actually explicitly modeled the bolt as shown right here. So we actually had steel properties, grout properties, and then the rock. And again, regardless of how we represent the bolt, when you put those reinforcing elements into the continuum model, they don't really make much of a difference on the ground behavior, much less than we know occurs in reality. And so the reason for this, we have to remember that the primary role of reinforcement is really to make the rock mass behave as a continuum by locking together blocks separated by discontinuities. But a continuum model, by its inherent nature, already enforces this constraint that the rock mass must behave as a continuum. So if we think of a graph, as shown here on the right, of basically how much the support is affecting the ground versus how much reinforcement we install, there's this portion of the curve where every little bit of support is doing quite a bit because it's helping tie together this rock mass into a continuum. But in a continuum model, that is already enforced, and we're basically just getting this portion of the curve here. So to summarize, why would we look at bonded block modeling as a way to study these stress-driven damage processes and rock support interaction? Well, with deeper and deeper excavations, we need new design tools. Continuum models have limitations in terms of simulating ground support interaction. And we need a discontinuum approach. And when it comes to the discontinuum approach you might select, I'm not here to tell you that bonded block modeling is necessarily better than any alternative approach, say using PFC or a combined hybrid finite discrete element method. It's one of many valid options to be explored, and it happens to be the one that we've been focusing on and have some promising results for. So with that in mind, there are three main questions that I want to address today. The first is, what are the physical phenomena that BBMs can reproduce, and how does it depend on the choices that we make during model development? Can we reproduce field scale behaviors of BBMs, and not just the peak strength, but also some of these other characteristics related to deformation and dilation? And then last but not least, can these BBMs reproduce the influence that reinforcement has on ground behavior, not just in a sort of a qualitative way, okay, more support means less deformation, but really quantitatively, can we reproduce this behavior? So before I go any further, I guess I should probably stop for a moment and let you know what I'm talking about when I say bonded block model. Basically, the idea is that we're representing the intact rock as a series of polygonal blocks. So these blocks are shown here with black lines indicating the contacts between adjacent blocks. Within the blocks, the material is represented as a continuum with finite different zones. And we can basically assign a continuum constitutive relationship to these zones within the blocks. So within the blocks, it's a continuum model, but basically as the block contacts fail, the individual blocks can detach and separate, and that's what makes it a discontinuum model. So I want to start by talking about some laboratory scale bonded block models, because of course that's the most well-constrained case to study. And I want to highlight the fact that we need to make some decisions related to how complex we want our model to be. So there are two questions. The first is, do we want to make the blocks elastic or inelastic? And in the context of a laboratory scale model, this is basically asking, do we want to allow inelastic deformation of the grains? So are we basically trying to simulate intragranular damage? And then do we want to use homogeneous or heterogeneous properties? Of course, it's simplest to just use one set of properties for all the blocks and all the contacts. But a more realistic approach would be to assign different stiffnesses to different grain types, as well as different contact properties for different pairs of minerals. Now, there's lots of different studies that calibrate models to different rock types, but the problem is that in the literature, there's basically studies that have different rock types and different types of modeling approaches. What there's really been a lack of is studies that take one rock type and compare how these decisions on complexity impact the ability of that model to replicate that one rock type's behavior. So that's what we spent some time working on. And what I'm going to present to you first is basically our most sophisticated model, just to illustrate some of the capabilities of the bonded block model. So what I'm showing here is that the bonded block model that we developed for the Creighton granite, which is what you saw on the previous slide, this is able to match not just the peak strength, including the curvature of the strength envelope, but also the stress damage thresholds, crack damage and crack initiation, as well as the residual strength. You can also see in the bottom right here, we're able to match the Brazilian tensile strength. And perhaps more importantly, something that I think is relatively unique, we were also able to match the post-peak stress strain behavior here. You can see the axial stress, axial strain, and volumetric strain, axial strain curves. And associated with that, we also see peak dilation angle being well matched. And as an interesting byproduct, as basically an emergent behavior of this model, we were able to observe the cohesion weakening, friction strengthening behavior of the granite, including this post-mobilization decay of friction angle as there's some asperity damage. And of course, mechanistically, we see that as we go from lower confinement to higher confinement, we have a transition in failure mode. And the way that that's represented in the model basically transitions from intergranular fracturing simulated by the opening of these contacts between blocks or grains, a transition from that to intragranular damage represented through this inelastic continuum model that we've assigned to the mineral grains. So that was the heterogeneous inelastic model, our most complex case. And what we showed is that basically you can replicate all of these observed behaviors of the rock. Now, if we look at these simpler cases, what we can see is that in both the elastic models, so the ones that neglected the potential for intragranular damage, these ones have difficulty replicating the higher confinement peak strength as well as the post-peak behavior. And the simple reason for this is that mechanistically, you have the most intragranular damage in brittle rocks at high confinement or in the post-peak region. And so if you don't allow that damage to be simulated, you can't replicate those attributes of the rock. The homogeneous inelastic model actually does relatively well, but it's not great at replicating the pre-peak damage. So the crack initiation and crack damage thresholds, the heterogeneity of the mineral grains at the lab scale really do control those thresholds. So with this in mind, we can now start to think about what it might mean for the field scale. And of course, at the field scale, things are a little different because your individual blocks no longer represent individual grains. So we have to make a few decisions about these. And the first is the block shape. Now, I don't think this is fully settled, but I believe there's sort of an emerging consensus that in 2 dimensions, you really need to use a Voronoi or polygonal block shape because that's what's going to give you the most realistic failure mechanisms in terms of the relative amount of tensile and shear damage within the rock. And it's also going to provide you the most realistic bulking behavior as illustrated by this plot on the right-hand side here. In 3 dimensions, though, when you add in the extra degree of freedom of motion, it turns out that you can actually end up with too much bulking or too much diligency when you use a 3-dimensional Voronoi configuration. And so it's much more common to use the trigon approach in 3D, which is basically using tetrahedra as your blocks. Now, in terms of block size, as I mentioned, at the field scale, it's not the same thing as a grain, but I also want to emphasize it's not the same thing as what we think of for a finite difference mesh. So it's not like, as you make your block size finer and finer, you will necessarily be getting a more and more accurate result in your model. And the reason is the finite difference mesh is a mathematical construct to basically help discretize a partial differential equation, whereas the blocks are really just a predetermination of the potential fracture pathways that can develop in the model. And so the most important thing with the block size is that it simply needs to be small enough that you're not imposing any kinematic constraints on where the fractures can develop. And so in practice, that basically means you tend to need a few dozen blocks along the edge of your excavation, and that tends to correspond to this range of block sizes historically. Now, in terms of the inelasticity and heterogeneity, at the field scale, what we found is that you really need to use inelastic blocks even for small confinement cases. And the reason is that if you're using a 10 centimeter, 20 centimeter, 30 centimeter block, we simply can't pretend that there's no damage occurring at finer scales than that. And so we need the inelasticity to account for that. Now, in terms of heterogeneity, it's quite common to use a distribution such as Weibull for the strengths of the contacts in the field scale bonded block models. I know this is something that Itasca does, but in our studies, what we actually found was that we didn't need to include the heterogeneity. We could certainly, but this added complexity was not necessary to replicate all of the behaviors that we observed in the field. So with that in mind, I want to finish off by taking you through a couple of case studies here. And the first is the Creighton mine one that I alluded to before. This is a deep mine in Sudbury, Canada, that's been producing nickel and copper since 1901. What you're seeing in the photo here is the face of the excavation, basically just as you're moving into the ore zone. Now, this is a deep mine, as I mentioned. When I was working there, it was 2.4 kilometers was the depth of mining. And so, of course, you have very high stresses, and that's illustrated here by all of these individual dots corresponding to microseismic events, and then the larger spheres, which represent strong ground motion events. The experiment that we conducted was performed on the 7910 level, so 7,910 feet below surface. And the idea was to install extensometers in this pillar here. We installed them from the 6300 drift on the left before the 6330 drift had advanced. So this allowed us to basically do a mine by as the 6330 drift went past the instruments. And then we also monitored to see how the pillar behaved as these 3 stopes were excavated. To give you a sense of the rock, we're dealing with the Creighton granite here, which is a strong brittle rock. The rock mass is also relatively massive. The GSI is on the order of 85. Because of the depth and the temperature, the joints here are pretty, well, they're few and far between, and those that do exist are pretty tightly closed, as illustrated in this photo here. And when you look at the photo on the right, you might say, well, Gabe, I don't know. I mean, are you sure that this rock mass is really that massive? It seems like there's some stuff going on in there. But a lot of what you're seeing is really these quartz veins here. And because the main granite matrix itself is relatively quartz rich, and these boundaries between the veins and the main rock are, there's no particular weakness there. These don't tend to really affect the overall behavior of the rock mass significantly. So once we had the extensometers installed and we're collecting data, we started to model this in FLAC 3D. You can see the modeled area here, and then a zoom in to the mesh of the extensometer instrumented pillar. This diagram on the right shows the sequencing. November 1st, 2013 is when we installed the extensometers right here. You can then see this stope was excavated next, followed by the mine by of the 6330 drift, and then subsequent mining in the surrounding stopes and drifts. What I'm showing here is the model result compared to one of the extensometers. This is a 6-anchor extensometer, so each one of the black lines represents the displacement or movement of one anchor over time here. The positions of the different anchors relative to the center of the pillar are shown here. These are distances in meters. And so we have 4 anchors on the right, and these correspond to rightward or positive displacement on this figure, and 2 anchors to the left, which correspond to leftward or negative displacement. And basically what I want you to take away from this figure is that we have a relatively good match between the model and the data over the course of the mining sequence. And B, again, this is an illustration of the fact that if you run this FLAC 3D model with no support, as shown in the red, or with support, as shown in the green, you basically get the same result. And again, I just want to emphasize that's not what's happening in reality. The support is doing quite a bit here. You can see A, that there is a lot of support in this photo, and B, that there's been quite a lot of rock mass bulking, enough to actually pretty severely damage the shotcrete. But clearly there's enough ground motion going on that it is activating some amount of resistance of this support. So because of this limitation in the representation of ground support interaction, we developed a bonded block model to study this case. Basically what we did, because it wasn't really realistic to model this whole area with the bonded blocks, we simply took a cross section at the area of interest where our extensometer was. We extracted the displacements at the top and bottom of the pillar from the FLAC 3D model, including the shear displacements. We then took those in 47 steps and applied them to the bonded block model per the mine sequence. We had these stress boundaries at the side initially before the adjacent drifts were mined, and then we removed them accordingly. And we also installed support per the mining sequence. And what you can see here is on the right, this is the same extensometer data in solid lines, and then the dashed lines are the bonded block model. So this is, again, a well-calibrated model. And we're seeing, the types of emergent behaviors that we would expect here. We have de-stressing of the spalled zones on the left and right of the pillar. The spalling is being modeled by the opening of these contacts, as shown by the solid black lines. And then we also have some finer scale damage occurring within the confined core of the pillar that's primarily being replicated in the model by inelastic damage within the blocks themselves. One interesting emergent behavior of this model is that when we looked at the peak strength of the pillar in the model, the ratio of that to the UCS was 45%. And if we compare that to the Headley and Grant empirical pillar strength prediction of 0.47, we're actually within 5% of the Headley and Grant predictions. So this is really interesting in that we weren't trying to calibrate the peak strength. we calibrated the displacement behavior, and the correct peak strength was an emergent behavior of the model. So with the model developed, we can then go in and test different support interaction cases. So we had our calibrated case with 3 bolts. We also have a case with 5 bolts. And we also tested an unsupported case. And you can see the results here in terms of pillar displacement. And we're getting something that looks a little more realistic here in terms of how the addition or removal of support would affect the pillar. But of course, I can say it looks more realistic, but we don't have any hard data in this case to compare. So that takes us to our last case study, which is going to let us look at this problem a little more quantitatively. So this is the Westcliff mine, which is an Australian longwall coal mine that was studied in detail by Caldwell. And what really makes this unique is that there are 2 pillars, Site A and Site B, that are basically identical in every way. They end up undergoing the same loading path and same material. But Site A had 2 bolts installed along its height, whereas Site B had 4 bolts. So this allows us to do sort of a direct comparison in our models. Again, we started with a continuum model. You can see the stratigraphy here, as well as the instrumentation that we were using, 1 extensometer, as well as a stress cell 4 meters into the pillar. And you can see that the extensometer measurements at multiple stages in the mining sequence were well replicated, as well as the relationship between the displacement right at the edge or rib of the pillar and the stress change observed on this stress cell a little further in. Now, when we look at the actual measurements in situ, we can see that the displacement at the boundary of Site A pillar, the difference between that and the displacement at the boundary of the Site B pillar is about 70%. So simply by adding 2 more bolts, going from 2 to 4, we have a 70% reduction in displacements. But in the continuum model, again, we see that that support effect is severely underestimated. So we developed a bonded block model for this case. Again, we used inelastic homogeneous blocks. And we elongated the blocks a bit so that we had some anisotropy to mimic the cleating fabric within the coal. We calibrated the model. Again, you can see matches the observations at the site quite well. And this is, I should say, the Site A results. So this is the case with 2 bolts. And once we had the model calibrated with 2 bolts, we had appropriate parameters for our coal material. We then added in 2 more bolts to replicate Site B, and we were able to observe that approximately 70% decrease in displacement. So this is the calibrated model for Site A, and then we simply took that Site A model, didn't recalibrate or change anything. We just added 2 more bolts, and we were able to quantitatively reproduce that decrease in displacement produced by the support. So to conclude, I just want to go back over these questions that I originally posed and the answers that we've developed. In terms of the phenomena that BBMs can reproduce, we found that if you introduce sufficient complexity into the models to replicate, the different physical phenomena that are taking place, then all of the observed parameters can be matched. Block inelasticity is really critical if you want to simulate confined behavior, and this is true at both the lab and the field scales. And while block heterogeneity is necessary to simulate crack development at the lab scale, we found that it was not needed at the field scale to obtain realistic results. In terms of reproducing field scale behavior, we showed that this is certainly possible. And in fact, the Creighton mine case demonstrated that calibrating just to displacements can actually provide correct strength as an emergent model behavior. Last but not least, can BBMs quantitatively reproduce the influence that rock bolt reinforcement has on ground behavior? Absolutely. And this is quite significant in that now if we have appropriate upscaling tools, we can calibrate models in the lab, upscale them to the field, and then predict how the rock might behave in response to different support designs. And this could be really useful during initial design phases. So that's all I've got for you today. Thank you so much for your attention. I really appreciate you all being here, and I look forward to your questions.
Thank you, Gabriel. Very interesting presentation. And it's good to have some extra time for you, or I was maybe delayed in the beginning, so I gave you a few minutes extra so we could conclude your presentation. Thank you. So now it's open for questions. I cannot really see in the chat. So maybe I could ask you to send your questions via the chat. And while you do that, I have one question for you, Gabriel. I understand that the BBM modeling has been used in your different cases in sparsely fractured and brittle rock mass. But if we are in a situation using the BBM where you have a fracture zone, for example, 30, 50, 70 centimeters thick, can you also model that with your BBM, or how would that occur?
Yeah, that's a great question. So, you know, the beauty of this method is that, again, because it's sort of based on fundamental, you know, physical principles, you can add additional components. And, you know, this is sort of the idea of the synthetic rock mass approach. So you could add in, say, you could have your intact rock BBM, and then you could add in or overprint a number of fractures over top of that. So you could replicate a dense network of pre-existing fractures. Depending on the scenario, it might be more appropriate to simulate that zone using basically a continuum inelastic constitutive model within the blocks, perhaps a weaker material. And that would, I guess, primarily be a question of scale. You know, how large is this zone relative to what you're modeling overall? But yeah, you know, we focus primarily on massive rock masses, just to, you know, isolate some variables and try to answer some questions in less complex cases. But certainly you can add in, you know, more pre-existing fractures to simulate those scenarios.
Okay, thank you. We got a question here from Ping Zhang, which is, when you talk about block inelasticity, could you give more details what constitutive model you have tried for?
Yes. Yeah, great. That's a great question. You know, we actually found that you don't need a very complex model for the blocks. We basically just used, at the lab scale, I believe we just used a perfectly plastic Moore Coulomb model. And we actually found, you know, in that most complex lab scale model, where I said it's heterogeneous and inelastic, the heterogeneity is actually only limited to the contact properties and the stiffness properties. So we did run a model where every mineral type had different strengths for the blocks, but we actually found that that added level of complexity, while perhaps more, you know, realistic technically, wasn't necessary. And so we sort of said, well, we'll go with the simpler model if it can basically do all the same things. And so that lab model just has one set of inelastic properties for all of the different grain types. And again, that's a perfectly plastic Moore Coulomb. At the field scale, I believe we're using a cohesion weakening, friction strengthening model within the blocks.
Okay, thank you very much. BBM is not very widely used in our country, and so I think people are curious about it. And of course, cost is always a matter of discussion, and what resources you have. So here, Rikard Gutel has made a question: what is the computational cost of BBM compared to other approaches in both modeling time and computer time?
Yeah, absolutely. I mean, it's a discontinuum approach, so it's expensive for sure. You know, it depends on how it's implemented, but I think, you know, the most common implementation of DBM would be in Itasca's UDEC software, which is what we use here. So it's definitely more expensive than a continuum model. It's probably less expensive than a hybrid finite discrete element model, but some of those softwares like Irazu from Geomechanica, they've done a lot of work on GPU optimization to speed up their codes. So, you know, it may actually be, you know, similar speeds these days. I would say for these models, they were generally taking on the order of a day to run. So, you know, it's not going to run super quickly, but it's also not sort of absurdly expensive. And I think the key thing that I would say is useful is this concept of doing, you know, mine scale or global scale continuum models, which is sort of, you know, relatively common now anyways. Do those type of models and then use this displacement boundary application approach that we demonstrated here, because running, you know, a bonded block model on a single pillar cross section is of course going to be relatively quick. Now, things in terms of computational costs can get out of control pretty quickly when you start doing three-dimensional models, and then you have all sorts of trade-offs between block size and model runtime. We haven't done as many of the 3D models in our group, but those ones, you know, are going to take you, you know, multiple days or weeks even.
Okay, thank you very much, Gabriel. We just got one more here. Very good. It's Ping Sang again. BBM modeling could simulate dilatation very well. How does block size affect the dilatation? For a field scale model, it means that the bulking calculation will be different. Could you give a comment on that?
Yeah, absolutely. That's a really great point. So, yeah, you know, we didn't look specifically at the influence of block size on dilation, you know, macroscopic dilation parameters, but we did do some analysis of block size influence on the behavior more generally. And sort of our takeaway, or how we're thinking about block size these days, is that you almost need to view it just as if it were another model calibration parameter. So we didn't see that there was like a very consistent trend. It's not like as you make your block size smaller and smaller, you're seeing more and more or less and less dilation. It's a little bit more erratic than that. So again, we really think of the block size almost as a calibration parameter. So the micro parameters that you assign to your model will be specific to the block size you use. Now, at this point, that's, again, a little bit of a limitation. I think ultimately the goal is that as these block size relationships and scaling relationships are better understood, that you can come up with reasonable predictions of which parameters are going to be appropriate for which block size.
Okay, thank you very much. We have some other questions. We need to close this session though, but we will address these questions after this session by mail. And of course, if you're interested in this topic, which seems to be a big group that is, remember to study and read the article that is at the website of Svenska Bergteknikföreningen. Thank you, Gabriel. Then I will just share screen with you. Let me see here. So now we go. Så detta var alltså det sista streamade webbinariet från Bergdagarna 2020. Och som ni säkert vet så finns artiklarna presenterade från webbinarierna på Svenska Bergteknikföreningens hemsida. Och det finns ju också inspelat då på föreningens YouTube-kanal. Så tipsa gärna era kollegor om dagens presentation, de som missar den. Och den kommer ligga då på Youtube-kanalen med största sannolikhet redan imorgon. Så tack för detta alla ni som deltog, och jag hoppas i ett annat forum så snart som möjligt. Tack ska ni ha, och på återhörande. Ha det så bra allihopa.